Welcome to qnawire.
Hi, so over here we're going to employ the following phase diagram in order to answer the next questions. In addition to this, we know that the delta H of fusion for xenon is going to be equal to 17.3 joules per gram, that the delta H of vaporization would correspond to 96.3 joules per gram, and the specific heat of the gas is going to be equal to 0.158 joule per gram Kelvin. So now, first of all, let's identify the phases on our phase diagram. This is going to be the solid, the liquid, and the gas phase corresponding to this system. The first question is what is going to be the normal melting point? It is going to be the transition between solid and liquid at 1 atmosphere. So it is going to correspond to 161.3 Kelvin. Normal boiling point is going to be the next point over here, which is going to have a boiling point of 165.0 Kelvin. At one temperature and pressure, the three phases can exist in equilibrium. This is going to be the triple point, and this is going to occur at a pressure of 0.37 atmospheres and a temperature of 152.0 Kelvin. Next up is xenon, a solid, a liquid, or a gas at room temperature and pressure. So at room temperature and pressure, we're going to have that we're at 1 atmosphere. Let's say that room temperature is around 20 degrees Celsius, so we would be at this point. And in this case, it is going to be a gas. Which is the more dense phase, the liquid or the solid? So in this case, to know which one is going to be more dense, we're going to look at the solid liquid phase line. If the slope is positive, that means that the solid is more dense, and it is characterized by a positive slope. If the slope is negative, as is the case for water, it does something like this. What is going to occur is that the liquid is more dense. So in this case, the solid is going to be more dense because the slope is going to be positive. And finally, we're going to have a 27.3 gram sample of liquid xenon that is going to be heated at constant pressure of 1 atmosphere from 165 Kelvin to 215.2 Kelvin. How much energy is going to be required in kilojoules? So over here we need to identify that our sample is starting here at the gas phase at 165 Kelvin, and we're going to increase the temperature. So the only contribution is going to come from the heat capacity of the gas. And also for, in this case, we're starting with liquid xenon, so we need to completely vaporize it. So we're going to have both of the contributions. So the heat is going to be equal to the mass times the delta H of vaporization, since we are having a liquid, plus the mass times the heat capacity of the gas times delta T for the gas. Note that delta T is going to be equal to a positive value, 215.2 minus 165, which is 50.2 Kelvin. So the heat required is going to be 27.3 grams times the delta H of vaporization of 96.3 joules per gram plus 27.3 grams times the heat capacity of the gas, 0.158 joule per gram Kelvin, times the delta T for the gas, which is 50.2 Kelvin. This gives us a total heat of 2,845.52 joules, or 2.84552 kilojoules, which would be our final answer. And with that, it would be all. Thanks and have a good one.